Okay, good morning, everyone. My name is Alexia Jones. I am the program manager with the MSCC Climate Science Program. And today we will have an introduction to I-WRF. And before we get started, I just would like to say, please be advised that this meeting will be recorded and may be publicly shared, including on platforms such as YouTube. By participating, you consent to the recording as its public discernment. All right, I would like to pass it to Jared Lee.
All right, thank you, Alexia, and good morning, everyone. So thanks for coming to and viewing this pre-workshop for the I-WRF student tutorial that we'll be having next week, 1 week from today on October 29th at Alabama A&M. So I look forward to meeting many of you there in person. So my name is Jared Lee. I'm a project scientist at the NSF National Center for Atmospheric Research in Boulder, Colorado. And this project about which we're having a tutorial, we're really a team of people from both Cornell University and NSF NCAR. Cornell is leading this project. Rich Knepper, listed here on the slide, is the overall PI or principal investigator of the project. And this is funded by NSF, the National Science Foundation, so I definitely want to acknowledge their support. And also thank you to MSCC for inviting us here to give this tutorial. So what I'm going to talk about here is kind of give a bit of an overview of, well, what is I-WRF? What are we going to be teaching you through this tutorial? So just kind of back up to first a 30,000 foot level. So really our overall goal here is we want to increase flexibility for weather research and really to help build a pipeline to recruit new atmospheric scientists into the field. And that's because weather prediction, it really is a vital part of our national capacity to support all sorts of different applications and industries. Weather impacts everything just about in our economy. It impacts trade and shipping. Forecasting impacts transportation. It impacts agriculture. It impacts public safety, both through air quality and through transport and dispersion. If there were releases of materials, whether accidental, say from train derailments, or intentional things from bad actors. It also has a huge impact on energy forecasting. It has an impact on stock markets. And also then beyond just the weather forecasting scales, then once you get into the sub-seasonal to seasonal to even climate scales, like many years out, then that sort of forecasting of the atmosphere or modeling of the atmosphere is also really important to inform policy, around climate change mitigation. It helps us do infrastructure planning, everything from where are we going to put power plants to how big do we need our storm sewer drains to be to handle maybe future increases in extreme rainfall events. It impacts insurance and reinsurance industries and a whole lot more applications than I've even listed here. And so modeling and simulating the atmosphere really is critical to the development of both daily and long-term weather analysis and prediction. And also, so that's our kind of our charge for why modeling the weather and climate is important. But we also do have a shortage of atmospheric scientists. And atmospheric scientists, it's a specialty field, and it requires a lot of training, both in theoretical and in technical domains. And we have a range of, I'll be talking on the career panel during the workshop as well. I can talk some more about this too, but you need to know a lot of math and physics, but also increasingly a lot of computer programming and machine learning and things like that. So there are a range of skills that are in need here. But so we're really interested in training the next generation of atmospheric scientists to come into the field. So one of our main tools to do this is WRF. And you may have been wondering, well, what is the WRF part of I-WRF? So WRF stands for the Weather Research and Forecasting Model. And it's a public domain weather model that's been developed since about the year 2000, led by scientists here at NSF NCAR, but also with a lot of support from universities, university researchers, and the U.S. Air Force initially, and so and NOAA, the National Oceanic and Atmospheric Administration. So there have been a lot of different funding agencies that have contributed to the development of this model. And now it has a user base of more than 30,000 registered users worldwide. I didn't look up how many countries the registered users are from, but it's well over 100. Most countries on Earth have registered users using WRF. And so it really is one of the probably the most commonly used weather forecasting model in the world. And it can handle both weather prediction and regional climate modeling. So it's used for both time scales of forecasting or simulation problems. It can simulate events based on changing the land cover in the model and seeing how that impacts the atmosphere. We use it to do chemistry and air quality problems, wildfire, renewable energy generation and forecasting, hydrologic forecasting like stream flow and reservoir management, crop growth modeling, aviation and turbulence, trying to keep pilots and passengers safe in the air, surface transportation, large eddy simulation, so kind of like urban scale modeling, and so much more. So it's really is a very flexible modeling system. And there are also validation and visualization tools that are available. It does take some work to connect those together, but there really is a mature suite of tools available. It's also been deployed across many HPC or high performance computing systems, such as supercomputers here at NSF NCAR and the Department of Energy and Department of Defense and all sorts of different systems. So we're able to include it in different benchmark studies. But there are some challenges with WRF. So at NSF NCAR, we run tutorials to help people learn how to use WRF and some of the other models as well that we've developed here. But surveys have shown that about half of users attending our tutorials, they report difficulty configuring the software for use on whatever computing platform that they're using. And I'm among that 50%. I've had through my career, especially when I was just getting started, or when I'm trying to do it on a machine that I'm unfamiliar with and I haven't been using before, it almost never goes perfectly smoothly. And that causes a lot of frustration because, like, as a scientist, I want to spend my time doing interesting science problems. I want to run my simulations. I want to do a bunch of the analysis. I'm not as interested in solving software engineering problems or fighting with compilers that because you have to, in order to go from source code to something that you can execute and run, you have to compile the code. And that's usually where the problem is. It's with the different compilers and the different libraries that WRF depends on. They also have to be built with the same compiler that you're trying to compile WRF with. And that can just lead to a lot of headaches. There are instructions on the WRF website for how to get around a lot of this, and that can help. But it can still be a time-consuming process and a really, really frustrating process, if I'm honest. And so we're very aware of that. And so in addition to, even once you get the software built, then you need to know, okay, where do I need to go get the data to use for my initial conditions and my lateral boundary conditions to kind of constrain the model, because the model isn't running over the whole globe. We have other models that do that, but for WRF, it's a regional model. You set up a domain over a particular box or rectangle somewhere over the Earth. So you need to specify, well, what are the winds? What's the moisture that's coming into the edges of my domain, or how do I initialize my domain? So you need to know, where do I find the data to start that, to configure the model. And also, like I mentioned, there are verification and visualization tools and packages available, but nothing's really plug and play. And so usually you have to do some work to write your own Python script or something like that to configure these tools to read it in properly, to plot it how you want it. And so there are a lot of technical barriers that students and researchers can run into that can really be discouraging before you even get to the fun stuff. So what we're trying to do is to really reduce those barriers, and that's why we proposed this I-WRF project to NSF. And so to get around or to mitigate a lot of these issues, there's something called software containers. These containers have already compiled in them all the associated libraries that are required. It has the source code it has everything you need in order to build the WRF code. So it really removes a lot of the headaches. We take care of in building the container and putting it up on a website that you can download. Basically, we're taking care of a lot of the issues to just make the process go more smoothly. And so basically, Ben will talk a bit more about this, but again, just as a one slide high level summary of the container, it basically runs what's called a virtual machine image or an image of a virtual machine on your computing system, whether that's a desktop or some high performance computing system or some cloud computing system. And Ben will also go into what those terms mean if you don't know them. So we're able to port the WRF modeling framework to a number of different systems. And so we include in these containers, we include the application for the WRF code, we include all the data that's needed to run these test cases. Everything's already configured for you so that hopefully it's just pressing a few buttons, typing a couple commands, but off you go. So we're trying to really make things as user-friendly as possible. And so these containers, they support simplicity, portability, and scalability. So we can run these containers on a wide range of systems without hitting the installation and configuration and compilation issues that are so prevalent. And so we also include data management and interoperability with both validation, verification, and visualization tools and packages. And so what this does is it allows for researchers to run large-scale problems with multi-node processing. And so again, really what we're trying to do is we're trying to lower the barrier so that we can help more researchers and especially students make the entry into atmospheric science to be able to focus on the science more quickly without having to deal with software engineering stuff. Now, if software engineering is your jam and computer science is your jam, that's great. We need you too. But for many of us, we don't want to have to deal with that. We want to deal with what we think is the fun stuff. So this allows the I-WRF containers allow you to model weather on your laptop, in the cloud, or on an HPC resource. Just one note of caution, though, that your laptop does not have the computing horsepower that cloud computing, say from Amazon Web Services, or that a high performance computer, say what NCAR has or what Cornell University has. And so to run the same problem will take a lot more time on your laptop than on a big supercomputer. So just keep that in mind. And so if you really want to run on your laptop, you're going to have to scale your problem down to still be something manageable. You can still do meaningful science on a smaller computer like your laptop, but if you have access to an HPC or cloud, that'll allow you to run a lot more simulations or a lot bigger simulations. So just to keep that in mind. So as part of this project, we have 3 science use cases that we were planning to demonstrate these containers on. The first one looks at land use land cover change in the northeastern US, and also looking at feedbacks to extreme weather events and societal impacts. The second one is, and this is one that I'm more interested in, or most interested in as someone who does renewable energy forecasting. So we plan to look at climate change impacts on wind and solar energy resources in the US. For instance, will there be changes in the frequency or the magnitude of wind and solar energy droughts in the US? When the wind isn't blowing or the sun isn't shining, we need to build an energy grid that can handle those sorts of conditions. So we want to ask the question: is that going to change? Or, looking now, what is that doing now? And how is that going to change, if at all, as we head toward the mid-century and late century, so that we can inform how we build out our energy system? And also third, the looking at changes in air quality in the northeastern US in the urban corridor from Washington, D.C. up through Baltimore, Philadelphia, New York City, Boston area. How is air quality going to change with a changing climate? And so before we even get to those bigger use cases, we decided to set up as kind of our test case zero, our entry level test to simulate Hurricane Matthew from 2016. Part of why we picked this is in NSF-NCAR's online WRF tutorial. This is the first simulation that they picked out for that. So we're just kind of paralleling that. So if you've taken that WRF tutorial, this case will look very familiar. And so again, what we're trying to do is make this WRF software easier to run and relevant to increasing recruitment into atmospheric science and building a pipeline of researchers, and also to bridge the diversity gap in weather and climate research. And here on this screen, I wrote the Python script, the visualization script to visualize the WRF output from this simulation. And so when Ben demonstrates the container next week, or if you follow the instructions to do it yourself, you'll end up getting graphics that look like this. Now, I've taken a bunch of still images and made an animated GIF out of them. But so you would get the still image version of it. But when you animate them together, this just shows kind of what the simulation will actually look like. On the left panel, we have sea level pressure. You can see the hurricane moving up the east coast of Florida, and then the 10-meter wind speed field in the middle. And then on the right panel is simulated radar reflectivity. So you can see in 3 different fields kind of just what the model is simulating. Now, this is a very coarse simulation so that it can run quickly in the span of a tutorial to just kind of get you going, but it at least gives you an idea of what the model is doing. And also we have for verification and validation, we use something called METplus, which is the model evaluation tools, and that was also developed here at NSF-NCAR with support from the Air Force and NOAA. And it's a verification framework that's very flexible across temporal and spatial scales, and it is used operationally for model validation and forecast verification by NOAA, the Australian Bureau of Meteorology, and other national weather forecast agencies. And it has a large community of users and contributors, and it was already containerized on its own. And so as part of I-WRF, we already have a METplus configuration for this Hurricane Matthew case. And then later on, as we get the other use cases developed, we'll have configurations for those as well. But this does some sample validation of the model against some observations, so we can see kind of how the model does and also make some plots from that. And that'll be part of the container demonstration as well. I hope these slides will be made available, but if not, you can always pause it as you're watching the recording of this. We have a bunch of resources here, links where you can start, visit our website and go through the tutorial on Jetstream, which Ben will be talking about more and then demonstrating next week on the 29th. But that's all I have, so thank you for listening. And if you do have any questions, you can either ask me next week when I'm at Alabama A&M, or you can either reach out to me via email, or you can send an email to this help@cac.cornell.edu as well, and someone from the team will get back to you. Thank you.
Thank you so much, Jared. Next, we will have Ben Trumbore.
Hello, good morning. Thank you for coming to this pre-workshop meeting. I'd like to talk a bit about the tutorial that we will be walking through at the workshop. And I want to give some background information on topics that may be unfamiliar to you or that you've heard of but don't know a lot about. I'm going to ask at the end that you do one important thing before the workshop so that we can make it possible for you to walk through the tutorial at the same time as we're demonstrating it, if you would like. It's not an obligation. But I want to start off. First of all, I'm Ben Trumbore. I'm a computational scientist at Cornell University's Center for Advanced Computing. We call it CAC. And I'm on this I-WRF project with Jared. And so I'm going to start off with an apology because I'm afraid that some of what I say here may seem patronizing to some folks who already know it, and it may not go into enough depth for other folks who are unfamiliar with it. So please understand we don't know the exact level of all the participants' experiences. So please be patient if it's something you already know. And if it's something you don't know about, at least you'll be aware that it is a topic that is relevant to this tutorial. So Jared talked about some of the aspects of trying to run WRF, and I'm looking at that here as well. So what do you need if you want to run WRF? Well, the first thing is you need a powerful computer. And as Jared pointed out, it's probably not going to be your personal computer. Now, it might work, might take a long time, but this is a good reason for us to reach over to the world of high performance computing and learn how to use those resources for performing these types of simulations. And once you have a computing environment that is sufficient, you need to install the WRF and METplus software. And as Jared said, that isn't an easy thing to do, but we have made that easier through the use of the containers that we'll talk about. It's much easier to install the containers on your computing resource than it is to try to build the software yourself. And then again, as Jared said, the data is a little confusing sometimes. So what data do I need? Where can I get it? How do I get it onto my computer? We'll go through that in the tutorial. And it's been made easier for this tutorial for the purposes of demonstration. And then, as Jared also pointed out, configuring these simulations can be a chore. The configuration file for the WRF process that we run in the tutorial is 129 lines long. Those are different parameters that are being set. And if you get some of them wrong, you're not going to get the results you want. So we'll have that all set up for you to run. And then, of course, if you want to run again with slightly different parameters, you need to take the additional step of learning what to do, what can be changed, what needs to be changed to run a longer simulation or a simulation on more processing power. But at least you'll have a baseline to start from, a simulation configuration that works. So one of the things I thought I would try to describe here is the different aspects of computing resources that you might have available to you. I'm expecting that everyone has a computer or has access to a computer, so I'm calling that your laptop here. And I'm comparing that to a HPC cluster and the cloud as computing platforms. A cluster is a large bunch of computational power that is running all the time. As opposed to your own computer, which you turn on and off when you want to use it. The cloud is very much like your own computer. You turn it on, you use it, and then you turn it off. And you only pay for it while you're turning it on, while it's turned on. And similarly with the HPC cluster, you're only paying for it while it's running your job. I got out of order here. Let's talk about paying for things. If you're buying a laptop, you usually have to pay for that up front, or maybe on a payment plan. But you're making a commitment to that expense right up front. And if your needs change and your laptop is no longer sufficient for the computation that you now need to do, you're kind of out of luck. And that's one of the main benefits of using an HPC cluster or the cloud. You only pay for it as you need it, as you use it. And if your needs change, then you change the way you use it and you pay accordingly. So that's a big selling point. And a lot of researchers have moved away from buying their own computers, trying to make them big and beefy. And in 8 years, they're not going to seem as big and beefy anymore. But if you instead get money to use the cloud or to compute on a cluster, that money will be usable in different ways as technology advances and computers provide new features for you to use, like GPUs for computation, for instance. Anyway, so as I'm saying here, when you buy your laptop, it is sort of fixed. It has the CPU that it will have forever, and probably the RAM as well. You might be able to add more RAM or disk space to it, but that's often a challenge. And with the HPC clusters in the cloud, you can have a larger CPU with more cores, and you can have more memory. If your data set is larger, you may find that that's a limiting factor, and you need to have more RAM to work with. So you can increase the amount you use if that's what you need, up to a point. There's still some hardware limitations about how many CPU cores or how much RAM is available, but it's going to be a lot more than you have on your own computer. And if you're working on an HPC cluster, you can usually ask for a number of CPU cores that is a multiple of the number of cores that are in each of the nodes, a physical component of the computational cluster. On the cloud, you can get a portion of the CPU cores that are available on one node. So you could have a small processing power of 2 CPU cores, or you could have 4 or 8, or usually it's a power of 2, up to the size of number of CPUs that are available on the node. And finally, another parallel between your laptop and the cloud is that you can have access to it whenever you want. You turn it on when you want it, you use it right away, and then you turn it off when you're done using it. An HPC cluster is a shared resource. It's always up and running, and multiple users are using it at the same time. And so you might have to wait in line to get your processing done. You enter your job into a queue, and the queue may be shorter or longer or faster moving or slower moving, depending on how much processing power you want. Whereas in the cloud, it's your resource only, and you can have it do what you want right away. So we're going to be running the tutorial using a cloud-based high-performance computing resource. And so cloud computing is often referred to as a form of virtual computing. And I just want to make sure that people have some idea what that means. So what is a virtual computer? Well, a physical or real computer has a lot of components in it. And it may be tough to sort out which ones are the essential elements of that computer and which ones are the peripherals. So I'm going to tell you now that the most essential elements of a computer are its CPU, central processing unit, the RAM, the random access memory, and the storage, which you might also call the disk space. If that's all you have, you still have a computer. The display, the mouse, keyboard, USB ports, whatever else you have, a camera, those things are peripheral. And so in the high-performance computing world, we really focus on the aspects of the computer that are essential. And so that's kind of what defines a virtual computer. So on a regular computer, like your laptop, let's say, there is hardware, physical hardware, and sitting on top of that is an operating system. It could be Windows, it could be Mac OS, or it could be one of the various flavors of Linux. And then on top of the operating system, you can run different applications, a web browser, a text editor, things like that. One of the applications that you may not be aware of, but which is available, is something called a hypervisor. And a hypervisor asks your operating system for slices of its disk space and its CPU power and its memory. And then it makes those available to applications that it can run. And those applications actually fire up another operating system. So you could have a Windows computer and run a hypervisor on it. And then you could, in that hypervisor, run a little Linux computer. This is actually built in right now in Windows, and I'm not sure about Macs, but it's a feature you might need to install or enable. But this idea of having a computer running within a computer is what we mean when we say a virtual computer. There is actually a physical computer down near the bottom of this process, but the virtual computer is up here at the top. And it's great because you could have as many of them as you want up to the power, the limitation of your computer, and you could change them. You could delete them and throw them away, or reset them back to their initial version if you've done things to them and broken them. So it's a very powerful bit of functionality. Now, somewhere along the line, people, if you take one quick look at this chart here, notice that remember that there's an operating system here and near the bottom. Somebody said, well, why? We don't really need to have an operating system running on hardware if what we really want to do is turn that hardware into a platform for only virtual computers. No desktop display or interactions with a particular user, but it's a platform for running virtual computers. And this is the way that cloud computing is designed. So what they did was they took away the operating system and they run a powerful hypervisor that is constructed for the purpose of supporting cloud computing. And then they made the hardware huge, lots of CPU cores, lots of RAM, lots of disk space, storage that can be sliced up and shared with the virtual computers that are running on it. And in the cloud computing world, we talk about these virtual computers, we call them instances. It's an instance of some operating system, some particular configuration on that operating system. You may have heard of some of the most popular commercial cloud platforms, Amazon Web Services, also called AWS, and the Google Cloud Platform, some people call that GCP, Microsoft Azure, and there are many others. For this tutorial, we're going to be using a cloud platform called Jetstream. It's Jetstream 2, actually. And it is based on a hypervisor called OpenStack. You probably haven't encountered that, but you will need to interact with OpenStack, even if it's a little indirectly, to create the instances that you want to run, the virtual computers, and to manage them. And we're going to do that interaction in this tutorial through a web interface called Exosphere. So there's a few more things you should know about cloud computing and cloud instances that often prove to be areas of concern for people. And the first one is that most cloud instances are going to run some flavor of a Linux operating system. And if you come from the Mac world or the Windows world, this may seem like an impediment to you. But it's important to have an open mind and be prepared to learn a bit about Linux. You'll need to issue some commands at a terminal, at a command line, to perform some of the operations in this tutorial. And hopefully you'll see that it's not that onerous. You can quickly learn what the commands are and how they're used. and there's lots of documentation available for them. It's a different experience than clicking on desktop shortcuts and then clicking in a user interface, but it's certainly not as hard as it may seem at first. We're going to be working with the Ubuntu flavor of Linux. Rocky and Alma are other flavors that are very popular, and these are all free to have running as the operating system on your cloud instance. Whereas Windows, you would need to have a license to run Windows or to run Red Hat, which is a flavor of Linux. These are not as commonly used unless it's an enterprise level application that's being run on the cloud instance. And the other thing you should know about cloud instances is that you're going to have to log into them in a way that's a little different than what you're used to. You don't sit down at the keyboard that's attached to your own personal computer and type in a password and you're in. You might need to you're going to need to issue some commands from your own computer to get logged into the instance once the instance is up and running. And sometimes you need to work with security key pairs, which we often refer to as SSH keys. These are a way of providing a greater level of security than a password gives you. And they're often required by different cloud computing platforms. I'm going to talk a little bit about that. It's possible that we will not actually use SSH key pairs in the tutorial, but it's an important thing to know about and understand to some degree, because if you try to work with a different high-performance computing platform, you may find that that is a requirement. So the way that you often log into a remote virtual computer or a high-performance cluster is using a program called SSH, which stands for Secure Shell. A shell is a command line environment where you can type commands. And a secure shell is one that is capable of performing communications with your computer, the remote computer. No, I guess the remote computer is the computing resource, but the communication between the two can be secure if necessary. And when you log in is a good time to have it be secure, so that you know that the computer knows that you're someone who is legally allowed to log in. So a key pair, and I have some pictures here from Wikipedia, is an encryption device that has two parts to it: a private part and a public part. The private part belongs to you, and you don't share it with anybody. The public part you can share with anybody, and you can put it onto your computers, the remote computers, and that will facilitate your ability to log into them remotely. And the way that works is that if you take some text string and you encrypt it with either the public or the private key and send it to the other computer, and it has the corresponding key, the public or the opposite key, it can use that key to decrypt the text string. And by comparing the string with what it expected it to be, can ensure that your private key matches the public key. It's a little confusing, I think, but it's really interesting. It's very secure, and all you need to do to use it is to know how to learn how to generate a key pair, and then make sure that the public part of that pair is with the person or computer that you want to communicate securely with, and then learn how to provide your private key when you try to connect to that computer or send an encrypted message. So I won't say much more about it. The Wikipedia page explains it pretty well. We may or may not be talking about that during this tutorial. So you may remember that Jared said that the I-WRF and METplus functionality, the applications, had been put into containers. They had been containerized. And that is the way that we are going to be using them in the tutorial. So I don't want to exaggerate this, but containerization is a form of virtualization that is not too different from the way the cloud computing environment works. What you need to do is install an engine on your computer. And there are two very popular types of containerization engines, Docker and Aptainer. We're going to be using Docker. So the Docker engine needs to be installed on our cloud instance. And once it is, you can download almost any of the containers that have been created for Docker, and they will run on your computer. And they will run on someone else's computer, even if it has a different operating system. It doesn't matter that you're on a Windows computer or a Mac, as long as you have the Docker engine there, it knows what to do with these containers to run them. Wonderful. The containers take care of all of the details of building the software and installing data files and configuring the little operating system that runs inside the container. You don't need to worry about any of that. So we're going to be working with 3 different containers in the tutorial. The one for I-WRF and the one for METplus have applications inside them, and we're going to run those containers. There's a third container that is essentially just a disk full of data. And once we download it, there it is. We just need to tell the other containers where it is if they have to talk to it. So looking ahead to the workshop itself, this is some information that I want to make sure you understand. During the tutorial, during the workshop, we are going to walk through a tutorial that is already available on the web. And Jared had a link to it at the end of his presentation. While we're doing that, we'll be happy to take questions from the participants about any aspect of it that they don't understand. We would also like to support you if you're in attendance and choose to try to follow along with the tutorial on Jetstream. So there's only the 3 of us that are going to be helping, depends on how many participants there are. If there's only a few questions, we'll certainly be able to keep up. But hopefully we can manage to help everyone get through the tutorial during the workshop. You're not obliged to try to do this, but we highly recommend that you do, because it's a great opportunity to where everything's laid out for you, and you have some assistance to get through it. If you don't choose to do that, you could also work through a very similar workflow tutorial that is meant for Windows computers, and at the workshop we'll give you the link for that. The Windows computers would need to have an Intel CPU in them. That's the only requirement there. You won't be able to do this on a Macintosh, a modern Macintosh. So we'll cover that. I want you to know now that you've got several options, and in particular, if you're doing the Jetstream, if you plan to do the Jetstream version of the tutorial with us or afterwards, there's something you'll need to do. The tutorials that you see online are still being refined, and some steps may change between the time to look at it, if you choose to look at it before the workshop, and when we actually walk through the tutorial. So please be aware of that. I don't recommend that you try to work through the tutorial before the workshop. It'll be better when the documentation is fully complete and we're there to assist you. So the one thing I would like to ask you to do is, if you want to work through the tutorial on Jetstream 2, you're going to need to get an account from Access, which is an organization that assists people with using certain high-performance computing resources, like Jetstream 2. So this link here is the webpage to go to. You should be able to create an account for yourself in no time. The next thing that will be needed would be to have an allocation of resource units, which are the computational dollars that will be spent while you run an instance on Jetstream 2. We're going to get an allocation for the attendees of the workshop to use, and we will want to link your account with that allocation. So we may be reaching out to you to get your access account information so that we can link those things up. We can also take care of that at the workshop if it hasn't been done beforehand. So please, without delay, if you think you'd like to work through the tutorial while at the workshop, please get yourself an access account. It should only take a couple minutes, and I think it will be generated immediately. So at this point, I'd like to turn things over to Lamai Weekly, who is on the Jetstream 2 team, and she's going to give us some more information about Jetstream.
Thanks everyone for to Ray and Alexia for having me, and thanks to Ben and Jared for their presentation and inviting me to talk about Jetstream 2. So so Jared walked you through I-WRF and the container that you'll be using in the workshop, and Ben walked you through some background about cloud computing and what you can hope to experience during the workshop. And as he mentioned, you will be doing the hands-on portion if you will be participating in it on Jetstream 2. So what is Jetstream 2? I'm here to talk about that. So my name is Lamai Weekly. I manage the Research Cloud Services team at Indiana University, and part of our charge is to provide support, education, outreach, and training for Jetstream 2. So what is Jetstream 2? Jetstream 2 is a flexible, user-friendly cloud computing environment designed for everyone from researchers with high-performance computing needs who might have minimal experience to software engineers who are looking for the latest in cloud-native approaches. And one other use case that's not outlined here in this slide is that we're also here for educators who have needs for their classroom as well. So as Ben mentioned, Jetstream 2 is a research cloud service, and the primary cloud is located here at Indiana University in our data center. But as you can see, we also consist of some regional clouds that are invite only, and that includes University of Hawaii, Arizona State University, the Texas Advanced Computing Center, and Cornell as well. So why Jetstream 2? Ben had a great slide that described the differences between your own laptop, HPC, and cloud computing. So why Jetstream 2 in particular as a cloud resource for your research or education needs? Well, it is an on-demand resource, as Ben outlined in his slide there. There are no runtime limits that you might encounter in the HPC environment. And you can launch your own virtual machines in minutes in a variety of sizes. So Ben mentioned that in cloud computing, you are getting a slice of a larger set of resources. And in this case, we have various resources available to you, from CPU only to GPU accelerated resources, large memory resources, and also some storage resources to go with your compute. And each instance comes with 1 terabyte of default storage. You also get full admin access to install software and instances and set up the environment how you want it on your instance. So you do have sudo, and you can install any software that you might need to do the research or educational use case that you have. We also have provide persistent IPs with full internet access, which is ideal for gateways and web hosting. Ben mentioned some use cases for cloud computing in his presentation, and indeed, web hosting or having a web server for either interacting with some of these research applications or talking about your research and having a way for students to interact with applications they might need in the classroom are available to you. And of course, it's an interactive computing environment with a graphical desktop, so it's available to you. You can spin this up at any time and have these resources available to you in a familiar graphical desktop environment. So what are the use cases that we see in Jetstream 2 that might apply to your research or research that you're mentor or faculty members might be working on, well, you can teach a course on Jetstream 2 and have workshops that are held on the Jetstream 2 as a resource. For example, the MSCC I-WRF workshop that you all will be participating in. This gives students access to powerful computing tools and also provides some virtual machines for training and analysis. You can also use Jetstream 2 to do some research software development. So you can work with your code, you can write, debug, and execute with interactive GUI applications, you know, the stuff that Jared was talking about that might not be the fun part of developing scientific applications, but it is available there so that you can code and compile against the most cutting edge resources and that are available to researchers in the nation. As mentioned, we also have GPUs. So if that's not available to you currently or not available at your home institute, we also have those available if you would like to train and refine and run some machine learning or AI workflows on Jetstream 2. You can also use it as a collaborative environment to share research or data with students and colleagues, either through a database that you host on Jetstream 2 or a portal where, again, people can interact with the application that you want to make available to your collaborators or your students. So what does it cost to use Jetstream 2? It costs nothing. As Ben mentioned, the commercial cloud providers that you might be familiar with do incur and do charge you for using their resources, but through the Access ecosystem, we are able to provide Jetstream 2 to any US-based researcher or educator at no cost. So again, this is provided through Access, which is an NSF-funded project that helps provision these NSF-funded HPC and cloud resources like Jetstream 2 to US researchers and educators. So how do you access Jetstream 2? All of access to Jetstream 2 begins with Access. So again, this is established and funded by the NSF, by the National Science Foundation, to help researchers and educators utilize advanced computing systems and services that are available to them here in the US. So you'll first need to go to Access, get your ID, as Ben mentioned, and then through that request an allocation. You won't need to do this for the workshop itself, but if you have interest or you think that this might be interesting to some collaborators or faculty collaborators, this would be the first steps that you would have to go through. And then before you log into Jetstream 2, you have to be added, you have to have your resources added, Jetstream 2 added to the resources on this active allocation that you will request. But again, we'll skip over that since we will be providing you with an allocation and you will have your resources for the workshop available to you there. So how do you get started on Jetstream 2? It's a simple 3-step procedure. The first step is to create your Access ID, which you will need to do if you would like to participate in the hands-on exercises in the workshop. So to do that, you'll have to go through this website, which is an Access website, and register for a new user, a new Access ID. There are 2 ways of doing that, which are to log on using your home institute's login, or to create a whole new identity. We recommend the second way to do that. It's just a little bit more foolproof and doesn't require you to sign in through your university and have some duplicate IDs out there. So we recommend the second way of creating your Access ID. Just navigate to that page and create one. You'll have to scroll down a little bit and to go to the second point, but just follow those instructions and you'll have your Access ID created in no time, as Ben mentioned. So the second step to creating your first Access project on Jetstream 2 is to request your allocation. There's 4 different types of allocations that you can choose from: Explore, Discover, Accelerate, and Maximize. And these have varying degrees well, first, you have varying levels of how much resources that will be made available to you, Explore being the smallest allocation and Maximize being the largest one. But they also have different a different process for each one to request and have it approved. So while the Explorer allocation might be the smallest allocation, it's still quite large for most people's needs. And the process for requesting that is very simple. It only requires a CV for the principal investigator on the allocation and an abstract, so a small paragraph describing what research or educational use case you'll have for your allocation. Graduate students can also be principal investigators on allocations. They'll simply need a faculty sponsor to request one. But again, for the workshop, we will be providing an allocation to you. But if you're interested in checking things out, please go on to the Access website and check things out. And then, of course, just get started. So we have a website over here, which takes you to the Getting Started over tutorial and guide that we have on our website. And if you go back to this former other slide, if you navigate to this page, it gets you to our website that gets you to that 1, 2, 3 steps. So let me just go there to share it with you. So if you click on that link, and again, I'll share these slides out with Alexia and Ray so that it can be available to you. You'll go to this website and just go through these 3 steps that I outlined on the slides. And finally, for upcoming events where you might want to find us and learn more about Jetstream 2 after the workshop, please head on to this website where you'll see all our events listed. Up soon that are upcoming are Getting Started on Jetstream 2 workshop on October 30th, Jetstream 2 in the classroom on November 6th, and of course you can join our Zoom office hours that take place every Tuesday from 2 to 3 p.m. Eastern Time for any questions that you might have about Jetstream 2, including how to get on it and how to get your access ID, etc. If you have any questions about Jetstream, please let us know, and you can reach out to us by sending an email to help@jetstream-cloud.org. This will create a ticket in our queue in the Access ticketing system. Or if you would like to peruse our documentation website, you can do so by going to docs.jetstream-cloud.org, and that's our documentation website where you can find all sorts of information about Jetstream 2, including what resources are made available to you, the Getting Started guide, and how you can start your journey with Jetstream 2. And that's all I had.
Awesome. Thank you so much. I did not realize I was on mute. Again, I just want to thank you all for your dedicated work in helping develop this student prep material. We will make sure that the students have access to this as soon as tomorrow morning. So that way they have a full week to prepare for your time together in person next week. Before I end the recording, is there any additional information that you all would like for us to add? We do understand that it is very important for the students to make sure that they watch this recording as well as follow the directions on the Jetstream slides.
I guess I don't have anything else to add at this point.
Awesome. Thanks, Jared. Well, we look forward to meeting you all in person at Alabama A&M next week.